Next example of subspace, let V is equal to M2 by 2R be vector space in the usual addition with respect to usual addition and usual scalar multiplication. That is, the addition of two matrices of M2 by 2 is the addition of corresponding element, and if I have to multiply by scalar, then multiply to each element by that scalar. Let W is equal to the set containing the elements from M2 by 2, that is 2 by 2 matrices of this type 0, B, C, 0. So these two elements are compulsory 0 and B and C are real number. Determine whether W is subspace of V. So when W is subspace of V, if W is satisfies the two conditions, clearly or obviously W is not equal to 5 and W is subset of V, as a 0, 0, 0 element belongs to W. This 0, 0, we can write another element from W, that 0, 1, 2, 0, 0 minus 1, 3, 0. These are the elements of W. So W has at least one element. W is at least one element means W is not equal to 5, and W is subset of V, because W contains the 2 by 2 matrices of this type. So these elements of W comes from M2 by 2 R. 2 by 2 matrices is the set of 2 by 2 matrices. Means this sentence is directly right. We directly write this sentence that W is not equal to 5, W is non-empty, and W is subset of that vector space V. Otherwise, W is not subspace of that vector space. Now we have to verify whether the remaining two conditions are satisfied by W or not satisfied by W. So first condition, we take two elements from W, any two elements. Suppose W1 is equal to 0, B1, C1, 0, and W2 is 0, B2, C2, 0. Belongs to WB any element, any two elements. Now we have to find their addition. So what is W1 bar plus W2 bar? Either take notation U bar and V bar, or W1 bar and W2 bar. So what is W1 bar plus W2 bar? 0, B1, C1, 0, 0, B2, C2, D2. And so add with these two elements by using usual addition, that is 0 plus 0 is 0, B1 plus C2, B1 plus B2, C1 plus C2, and 0 plus 0 is 0. And this is the element of W, because this element is of this type 0, B, C, 0. What are these? B1 plus B2 and C1 plus C2 are real numbers. So obviously W1 plus W2 belongs to W, and therefore we say that W1 plus W2 belongs to W for all W1 and W2 belongs to W. Why is true for all? Because these W1 and W2 are any two element of W, and their addition belongs to W. Means addition of every two elements belongs to W. Then we say that W1 bar plus W2 bar belongs to W for all W1 and W2 belongs to W. Now the second condition, we take the W, one element of this W. So suppose W1 is equal to 0, B, 0, 0, B, C, 0, and K be any scalar. So this is the element of W, W1 at 0, B, 0, C, 0, and K be any scalar. Then what is K into W1? Then use the multiplication of scalar multiplication, that is multiply this K by each element. So K into 0 is 0, KB, right, B, not B1, and then KC, and 0 into K into 0 is 0. And this is again the element of W, because this is the element is of this type 0, B, C, 0, and it is 2 by 2 matrix. So it is the element of W, and therefore what we have, KW1 belongs to W, right, W for all W belongs to, for all W1 belongs to W, and for any scalar K. That is the second condition. Any scalar and any element of W, their multiplication belongs to W. So, and why it is true for all W1? Because this W1 is any element of W, and it is true for that. So we say it is true for all element of W. So KW1 belongs to W for all W1 belongs to W, and for any scalar K, and therefore W is a subspace of W. W is a subspace of V. This set is a subspace of V, because this set satisfies the two conditions. Now next example, V is equal to M2 by 2 RB vector space in the usual with respect to or corresponding to usual addition and scalar multiplication in M2 by 2R. Let W is equal to the set ABCD, that is the set of order set of 2 by 2 matrices, such that ABCD are integers. And now we have to show, we have to determine whether W is subspace of V. So if we take the first condition, that is the addition of two elements of W belongs to W, then the condition is true for W. Addition of two elements of W is again the element of W, because addition of integer to integer is integer. That's why the first condition is true for W. Because if you take the element, suppose W1 as A1, B1, C1, D1 as the 2 by 2 matrix, and is W2 bar as A2, B2, C2, D2, then its addition is A1 is again the 2 by 2 matrix, A1 plus A2, B1 plus B2, C1 plus C2, D1 plus D2. And A1, B1, C1, D1, A2, B2, C2, D2 are integers, and the addition of two integer is again integer. So W1 bar plus W2 bar belongs to W. That is, this condition is true for this set. This condition, W1 bar plus W2 bar belongs to W for all W1 belongs to W1 and W2 belongs to W. But the second condition is not true. So how we can, this condition, that is any scalar and any element of W, their multiplication not necessarily belongs to W. So I have to write the counter example. So take K as 1/2 and W as the element 2, 3, 4, 5 belongs to W. Then what is K into A? K into A, or this, suppose this A, write the notation for this matrix as A or W1. Okay. So K into A, suppose this is A, right here, A notation, A is equal to this matrix, is the element of W. Then K into A is what? 1/2 into this matrix. Is 1/2 into 2 is 1, right here 1. 1/2 into 3 is 3 by 2. 1/2 into 4 is 2. And 1/2 into 5 is 5 by 2. So this is K into A, right? This is A equal to S, W belongs to W. And this is does not belong to W, because this is 2 by 2 matrix, but these entries 1 minus 3 by, this is 3 by 2, 2 and 5 by 2, all are not integers. So what is the condition when any 2 by 2 matrix belongs to W, if its entries are integers? So these are not integers. 3 by 2 is not integer. 1 is integer, 2 is integer, but 3 by 2 is not integer, 5 by 2 is not integer. And so K belongs to W for all A belongs to W. For all A belongs to W, W is not closed. So KA does not belong to W right here. For KA does not belongs to W right here, does not. Or this condition is not true for W, that KA belongs to W for all A bar belongs to W. So this is not true for W. Right here, either KA bar does not, right, not belongs to W. This is not belongs to, right here, the notation does not belongs to W for all A bar belongs to W. And therefore W is not closed for scalar multiplication. And so that property, second number property, is dissatisfied for W, and therefore W is not subspace of V right here, V, this V. W is not subspace of V. W is not subspace of V right here, V. So if we take K as 2, suppose K as 2 and W as this element, then what we have, that K is 4, 6, 8 and 10, and it is the element of W. So don't take K as an integer. Take K as a scalar, means any number. So we have to take the K as a fractional number. It's real number. K is a scalar, means K is a real number. Here K is for any scalar K. So K is a scalar, means K may not be, K is what? K is real number. It may be a fractional number. So we take as a fractional number. So for fractional number, it is not true. Okay. So take K, value of K and this A as a element of W in such a way that K A does not belong to W. Okay. So this is the counter example for condition second fails for this set, and therefore this set is not a vector, is not subspace. So in order to show the set is subspace, we have to prove the two conditions. But if in order to show the set is not subspace, we have to give the counter example for any one condition out of the two conditions. That the condition we have to show the out of the two, one condition fails for the set. And so in order to show the set is in a subspace of V, we have to show the two conditions, or either we have to show the set is not subspace, that is, so the first condition or second condition fails, either by using counter example or general example. So next example is V is equal to C, 0 1, set 0 1, close interval 0 1 R. That is the set of all continuous functions from close interval 0 1 to R. V is the set of functions. Vector space of all continuous real valued functions defined on close interval 0 1. What is this V? V is the, this is the notation C in curly bracket close interval 0 1 comma R. That is the set of, or is the vector space of all continuous real valued functions. That is all continuous functions from close interval 0 1 to R. And W is obviously subset of V. W is the set F belongs to V such that F of 1 half is equal to 0. Show that W is a subspace of V. So the elements in W comes from this set V. F belongs to V such that the F of 1 half is 0. So functions from V under which the image of 1 half is 0. So we have to take the functions like this. And then we have to show that W is subspace of V. So clearly W is subset of V, and W is not equal to phi, because why W is subset of V? Because the elements of W comes from V, and it is not equal to phi. Now we have to show the two conditions. We have to show the first condition, that is addition of two elements of W belongs to W. So first take two elements from W. Let F and G belongs to W. Now W or V is the set of functions. That's why we have to take the notations as F, G, H, I. These are the notations for the elements of W or V. So let F and G belongs to W, be any vectors, be any elements of W. Now what do we have? F of 1 half is 0, G of 1 half is 0. Because F and G are the element of W, means F and G both satisfies this condition, that F of 1 half is 0, F G of 1 half is 0. Now we have to show F plus G belongs to W. So when F plus G belongs to W, if F plus G satisfies this condition, that is F plus G 1 half is 0, then we say F plus G belongs to W. So consider F plus G 1 half is equal to F of 1 half plus G of 1 half. And F of 1 half is 0, G of 1 half is 0, and 0 plus 0 is 0. And therefore F plus G belongs to W, because F plus G 1 half is 0. F plus G satisfies this condition, and therefore F plus G belongs to W. And therefore we say F plus G belongs to W for all F and G belongs to W. This is the first condition. Now we have to show the second condition, that is any scalar and any element of W, its multiplication belongs to W. So let F belongs to W be any element and K be any scalar. K be any scalar. Now we have F of 1 half is 0, as F belongs to W, and therefore F of 1 half is 0. Now consider Kf 1 half, because we have to show Kf belongs to W. So for that we consider Kf 1 half. So it is K 1 half, Kf of 1 half. This is by using the definition of scalar multiplication in functions. So Kf1 half is Kf of 1 half, and f of 1 half is 0, and k into 0 is 0. Next step, k into 0 is 0. And so Kf1 half is 0, and therefore this k belongs to W. And so what we have? K belongs to W for all f belongs to W and for any scalar k. And therefore W is subspace of V, because W satisfies both the conditions, and therefore W is a subspace of V. So this is the example of function. So these examples are important as far as the exam concerned. Now we have to solve the some another examples, more examples on this topic. So we'll see more examples on this topic. So exercise on this topic. So we will see the more examples on this topic and some exercises. So for any vector space V, singleton 0 bar. So the set contains only 0 vector from V, and itself a V are the two subspaces of V. So these subspaces are called trivial subspaces of V. So for any vector space V, itself V is a subspace of V and singleton 0. That is, the set contains only 0 vector from vector space V. These two are obviously the subspaces of that vector space V and are called trivial subspaces of V. So, or is are called improper subspaces of V. And other than these, the remaining vector subspaces, if the vector space has some another subspaces, then are called proper subspaces. So singleton 0, that is, the set contains only 0 vector from V, is the subspace of any vector space V, and V itself, every vector space is subspace of itself, and these two vector spaces are called subspaces are called trivial subspaces, or zero subspaces is also called zero subspaces. Singleton 0, these subspaces are called trivial subspaces of V both, and this singleton 0 is called zero subspace. So determine whether W is equal to the set x, y, z such that x plus y plus z is equal to 1 is subspace of R3. We know that this is not subspace of R3 because this is the linear combination of x, y, z. So is equal to 1. If it is equal to 0, here is equal to 0, then it is a subspace. But if it is equal to 1, so in general, W is equal to x, y, z such that x plus by plus cz is equal to 0 is subspace. But x plus by plus cz is equal to any non-zero element, then it is not subspace. Here x, y, a, b, c are 1, 1, 1 and is equal to 1, it is not subspace. So we can show how it is not subspace, either showing the counter example, giving the counter example for the condition number 1 or condition number 2. So both the condition fails for this set. For this set, both the conditions, that is addition of two element of W is not element of W. So take the first one element of W as 1 0 0 is the element of W. Suppose in round bracket 1 comma 0 comma 0 is the element of W, and 0 1 0 is the another element of W, because x plus y plus z is equal to 1. And if you add these two elements 1 0 0 and 0 1 0, then its addition is 1 1 0, and it is not element of W because 1 plus 1 plus 0 is not equal to 1, is equal to 2. So by using counter example, we can show that addition of W, two element of W, is not element of W. Similarly, we can show the second property also fails. Take scalar and take one element of W, their multiplication is not element of W. For example, if we take element of W as 1 0 0 and the scalar as 2, then 2 into this element 2 1 0 0 is 2 0 0, and it is not element of W. So both the condition fails for W, and therefore W is not subspace. Either give any one condition counter example for any one condition, or we can also give the example answer of this example in just one sentence, that 0 0 0 does not belong to W. Why? Because 0 plus 0 plus 0 is not equal to 1. It is not element of W, and W is not subspace of R3, and therefore W is not subspace of R3. Actually, what is the, when W is subspace of R3 by using definition, when W is subspace of R3, if W is itself a vector space, and when W is itself a vector space, W satisfies the 10 axioms of vector space. and the A3 axiom is what? Zero vector must be exist in that vector space. So W is zero vector is not zero vector of W is what? 0 0 0, this three tuple, and this is not the element of W, and therefore W is not subspace of R3. So we can give the answer of this problem in three ways. Either show the condition first fails, that is U bar plus V bar does not belongs to W for some U bar and V bar belongs to W, or the second condition K into U bar does not belongs to W for some K and for some U bar belongs to W, or the third method is what? 0 0 0 does not belongs to W, and therefore W is not a subspace of R3. Similarly, the next example is V is M2 by 2R, the vector space of all 2 by 2 matrices with real entries and with respect to the two operations usual addition and usual scalar multiplication. That W is set of all 2 by 2 matrices of this type A 0 0 B. AB belongs to R, then W is subspace of V. So how can show W is subspace of V? We take two elements. Suppose these are the two elements from W, this set like this, and their addition is again the same type element, and this is the element of this A plus B belongs to W, and then Ka, that is take A as A00B, then K is this again the element of W. So we show that both A plus B and K are again in W, and therefore W is subspace of V. So mm, so we can show the set this again the example f is V, f of 1 half is 0, then show that W is subspace of V. Already we have seen this example, that is to take two elements from W and their addition belongs to W, and take any scalar K and f as the element of W, then Kf also belongs to W. So these are some examples of the subspace. So we'll see the remaining examples in the next lecture. This is also we have seen in the last lecture that V is R3 and W is the set X, Y, Z belongs to R3 such that 2x plus 3y plus 4z is equal to 0. Then W is subspace of V. But if 2x plus 3y plus 4z is equal to some non-zero element, suppose 1 or 2 or minus 1, 3, then it is not a subspace. We know that. So this is the subspace because it is closed for addition and closed for scalar multiplication. The two conditions are satisfied by this W, and therefore this set is a subspace of R3. So the remaining example we will see in the next lecture. Example of subspace we will see the next lecture.